this lecture, I'm going to continue a conversation about variation. We're getting more of the mathy details of variation here. Specifically, we're going to talk about direct variation and some subtopics within direct variation. Direct variation with powers and direct variation with roots and cubed roots. The prerequisites that you need for this lecture would be a familiarity with solving linear, quadratic, cubic, square root, and cubed root equations. Now, if you've already gone through functions, that would also be a great prerequisite, although it's not necessary to be able to do variation problems. But I'm going to be using function notation possibly, and I'll mention the word functions like I already have several times. I'll first start by defining what directly proportional means. Two variables that are related to one another via some type of equation are called directly proportional if the ratios of their corresponding values are always the same. What does this mean? Well, suppose that you rent some type of U-Haul or rental truck or something like that, and they charge by the mile. So if you travel 10 miles, let's just pretend they charge you, I don't know, let's say $5. And if you travel 20 miles, let's say they charge you $10. And if you travel 25 miles, they charge you $12.50. And so on and so forth. So you can just get a list of values. Now this table is given to you in this problem. It's not that that you have to figure this out. Somebody just hands you a table and they ask, are these two variables, miles, M, and the charge, C, are those two variables directly proportional? Well, you go ahead and take their ratio. And actually, it doesn't really matter which way you do it as long as you're consistent. So if you want to look at C over M, you could do it that way. Or if you want to look at M over C, you could do it that way. As long as you're consistent, it doesn't really matter. So if you did C over M, for example, you get 5 out of 10 for at least for this first row, which when reduced is 1/2. If for the second row you would have gotten 10 out of 20, which when reduced is 1/2. And again, for the third row, you'd get the improper fraction 1250 over 25, which when reduced is again 1/2. Notice that all these ratios are exactly the same. So this means that these two variables are directly proportional, or they're proportional. That's another way we say this. And again, like I said, you could have, if you chose to look at M over C, that's absolutely fine as well. M over C would have been 10 over 5, which is 2, or 20 over 10, which is 2, or 25 over 1250, which is 2. As long as you're consistent, it doesn't really matter. Notice that all these ratios end up being the same for this column. So these two variables are known to be directly proportional. Now, what is so important about two variables being directly proportional is that a lot of things in real life center around variables that are actually directly proportional. And we can say a lot of things about variables that are directly proportional. It makes math a little bit easier if variables are directly proportional. And really, when somebody says that these two variables are directly proportional, you want to be able to interpret what that means. And of course, that leads us into this definition of direct variation. We say that a variable varies directly with another variable. So in this case, y varies directly with x. If you could write it in equation form, y equals some number times x, where that number k is a positive constant called the constant of variation. You can also see that written as the constant of proportionality. Sometimes people call it that. So it just depends on what textbook you're using or what mathematician you're talking about or who's talking to you about it. Some people just say that it varies with it when they really should say it varies directly, by the way. We'll take a look at a simple example here. A person earning $15 per hour has a weekly wage defined by the equation W is equal to 15H, where H is the number of hours she works. So if she works 1 hour, 1 times 15, that would be $15. If she worked 2 hours, that'd be $30, and so on and so forth. These two variables vary directly. In fact, the constant of variation here is 15. Now, in reality, there are a lot of things that we think are represented by variation that are actually not represented by variation. Prime example of this is the cost to rent a U-Haul, which is about $19.99 or maybe $19.95, I'm not 100% sure, plus 50 cents per mile. If you write that equation down, the cost is $19.99 plus 50 cents per mile. This could be variation if and only if it was this, C equals 0.50 m. That's direct variation right there, because C is equal to something times our variable. Remember, direct variation is given by y equals kx, where k is called the constant of variation or the constant of proportionality. And in this situation, when I say this situation, I mean the actual real situation we're talking about, it's not just C equals something times m, it's C equals a number plus something times m. So this is definitely not variation. So you have to be very careful, even though it has sort of the feel of direct variation, where as the cost increases, so do the number of miles, or as the number of miles increases, so does the cost. It's definitely not variation. And that's why in my previous video, when I talked about the concepts of variation, when I defined direct variation there, I said this is technically not the real definition of variation, because we have some other little bits we'll have to add on. And this is that little bit, that it's not direct variation just if one variable increases, the other variable increases. They both have to start at 0, 0. And maybe I should write that down. That's incredibly important. To truly represent direct variation, not just direct and inverse, but only direct. To truly represent direct variation, y must equal 0 when x equals 0. In other words, y is equal to some number times x, because in this case, if x is 0, it forces y to be 0. Of course, it doesn't have to be y and x you're talking about. It could be c and m. C has to be some number times m, or r has to be some number times L, or something like that. Doesn't really matter, but as long as when one variable is 0, it forces the other variable to be 0. That is direct variation. And as we can see back in this previous example, this equation that's been highlighted is not of that form. When m is 0, c is not 0, it's 1999, so this cannot be direct variation. Now I want to draw your attention to kind of the graphs of a direct variation situation. We'll go back and talk about that wage example where we said that a person's wage is, they earns $15 an hour, and so their wage is just 15 times the number of hours they've worked for that week. If you graph this equation, you can easily tell right away, because you should have experience with this, that this is a linear equation in two variables. The output variable we're going to call W, the input variable we'll call H, and if you graph this, you can either build a table, or you can notice that this is of the form y equals mx plus b, the slope-intercept form, where in this case b is 0. So in other words, our y-intercept is at 0. I'll go ahead and plot that. And our slope is 15. So that means that I would rise 15 and run 1. So I'll just pretend, because I don't have scales on these axes, I'll pretend that this is an input value of 1 when this is an output value of 15. So I rose 15, ran 1. Let me label this point as well. That's 1, 15. When you connect the dots, you'll see you get a nice line. I'm really trying to be straight with my graph here. Something like that. When you connect the dots, you get a nice beautiful line that goes through the origin. And that's super important to note, that all direct variation problems, their graphs are straight lines or lines that go through the origin. This theorem that I'm just quickly written up is just for the graph of direct variation, not inverse, but direct variation, which is all about what this this lecture is all about. If y varies directly with x, that means y equals some number times x, then the graph that represents this variation is a line having slope k going through the origin. And that is represented in this previous example here, where we have a direct variation, w is equal to 15 times h, and when we graph it out, it actually is a line with slope 15 that goes through the origin. Super important because when somebody hands you graphs and they want to know, hey, are these variables directly varying with one another, or directly proportional, or directly related to one another, whatever language they use, you could quickly determine if they are or are not directly related or directly proportional or varying directly with each other just by looking at it and saying, oh, it's a line that goes to the origin. If it doesn't go through the origin, they're not directly related or proportional or varying. Let's go ahead and take a look at an application example. And this application example is not truly very realistic. There's a ton of applications that are real applications for direct variation. But let's go ahead and deal with one that at least has something to do with education. The students' score on their exam is directly proportional to their average homework score. Now, remember how I always treat problem solving, like word problems applications, is that I have this rule of thumb that you should always follow when you're trying to solve an application problem. The first thing you should do is read the problem. That's obvious. The second thing you should do is truly try to understand what's going on in the problem. So I'll write that out here. Third thing you should do, label your unknowns. Identify and label unknowns. The fourth thing you should do is write an equation or two, or three, or four. So I'll just say write equations involving these unknowns. The fifth thing you should do is solve these equations or answer the question, whatever it is that's being asked in the problem, and then state your results finally. And I'll write check and state, even though I generally, on an online lecture, do not check my results, but you should. You should check your results and state your results. Alright, so like I said, a student's score on their exam is directly proportional to their average homework score. A student who has an average homework score of 78% will likely score 75% on the exam. Now, they want us to express the exam score as a function of their homework score. So in other words, we want E equals some junk with H. That's what expressing the exam score as a function of homework score means, is that E of H is equal to some junk with H. You could probably see that E is a function of H, which means exam score is a function of homework score. Often, when I'm doing a variation problem, I don't write that of H business. I just write E is equal to. And then I'll use the fact that, so I've read, I understand what's going on. I'll use the fact that they've given me letters for the unknowns. E is for the exam score and H is for the homework score. And to write the equations, I happen to know this is direct variation because they say directly proportional, which means that the exam score is K, some number, times the homework score H. E equals KH. So this is actually the answer for the main paragraph. E equals KH. Now, how do we find K? This is our first foray really into an application direct proportion or direct variation problem, but they all kind of work like this. Somebody says, hey, these two variables are directly proportional, so you create an equation, E equals KH. It's that quick. And then they ask you some type of question about this equation, and you have to use some information they've given you. Specifically, they give us that a student who has an average homework score of 78% will score 75% on the exam. That is our link to get what the value of K is. We don't know that value of k, so they say to us that, hey, listen, by the way, stupid, if they get a 75% on the exam, so E is equal to 75, then they'll get a 78% on the homework. H is 78. And now you see in this equation right here, we only have one unknown, and that is k. So I'll divide both sides by 78. So this will imply that k is equal to 75/78. Now, I do not think that reduces. Actually, it does reduce now that I'm looking at it. That's like 3 times 25 over 3 times 26. The 3's are common factors. 3 over 3 is just 1. So this is going to be 25/26. So in this case, this is the relationship between E and H. And in fact, our equation, I'm going to replace this k here with 25/26 to get that E is equal to 25/26 H. That is our equation for direct variation for this problem. And now, whenever they ask me a question, like in parts A and B they will, I can answer using this equation. For example, what will Bill's score be on the exam if his average homework score is 43%? So for part A, I will let H equal 43. So we get this business. E is equal to 25/26 times 43. Now, in this case, I would tell you right now that I would prefer to use some type of calculator here because I don't want to have to do this all by hand. So I'll do this 25 times 43, let's see, divided by 26. So 41.3, let's just pretend. So I'll write this out here. Roughly equals, it's not actually equal to, it's roughly or approximately equal to 41.3%. That is what their exam score is going to be if their homework score is 43%. Now, obviously, this is not too realistic. I have students that get very low homework scores but get high exam scores, but more often it's the case that somebody gets a very high homework score and yet their exam scores are pretty low. So this is not really a true rule, but it's just a problem that we can kind of fiddle with here. Now, what was Bill's average homework score if he scored a 92% on the exam? Now, I'll keep the calculator out. What was Bill's homework score if his average exam score was 92%? In other words, we're going to let the exam score equal 92. So we have 92 is equal to 25/26, and this time we just don't know the homework score. This is an equation involving a variable, it's an equation involving a fraction, so I'm going to multiply both sides by the denominator of that fraction first to get rid of that denominator. So multiply both sides by 26. I know you guys should know how to do this, but sometimes I like to take my time. And now I'll divide both sides by 25 as well. When you do that, you'll get that H is equal to 26 times 92. Maybe I shouldn't use that dot notation. I'll use a parenthetical notation. And again, I'm dividing both sides by 25, so divided by 25. I go the handy dandy graphing calculator here. I say 26 times 92, and I'll divide that by 25. I get 95.7 roughly. And that should make sense because we have such a high exam score, our homework score is likely high as well. As a final example for some of these simple application direct variation problems, take a look at this. The weight of an object on the moon varies directly with its weight on Earth. A person who weighs 150 pounds on the Earth would weigh only 24.75 pounds on the moon. It's a smaller object, so therefore it has less gravitational pull. So first of all, they're not really asking me anything, so maybe I should probably ask a sub-question here. How much would you weigh on the moon? I like this kind of question where I'm not telling you what to plug in necessarily. Instead, I'm just saying how much would you actually weigh on the moon? The first way to answer this question, the first step to do this, is to notice that these variables, the weight of an object on the moon and the weight of an object on Earth, directly vary with one another. So we're going to let W sub m equal weight on the moon. And I know some people will like to use x and y. That's absolutely fine. I like to use variables that kind of represent the situation. So it just seems correct to me to use w's for weights, and I'll use the sub m for the moon and sub e for your weight on the Earth. And it says, okay, so the weight of an object on the moon varies directly. That means equals some number with the weight on the Earth. So some number times w sub e. Weight on the moon is some number times the weight of the Earth. Now, to find out what that number is, what k is, we'll have to use some information they've given us. And this is actually how it's always been done to find out how two variables vary with one another, what that constant of variation is that they take some sample and they say, okay, it seems that when you're 150 pounds on the Earth, you'll be 24.75 pounds on the moon. That will allow us to find the link between those two variables, and then we can forever use that link. So the weight on the moon is 24.75 pounds. I don't need to write that in. Equals k times the weight on the Earth, 150 pounds. And again, I'm not writing the words pounds here because they're the same units. I know that when I divide by 150 pounds, the words pounds will end up canceling, so there's no point. Now, if we were talking pounds and ounces, I would likely write in the units so that I can do some unit conversion, but no need here. Anyhow, this implies that k is going to be 24.75 over 150. And this is not really a proper fraction at all because it's a decimal number over a integer or an integer. But if you were to plug it into your handy dandy calculator, you'll get that k is equal to 0.165. So now I know that a person's weight on the moon is equal to 0.165 times their weight on the Earth. Now remember, 0.165 multiplied by a number will shrink that number, so that makes sense. If you weigh 150 pounds on the Earth, your weight should be less on the moon. Now, how much would you weigh on the moon? Please substitute in your weight. I'm going to substitute in mine, but you could substitute in yours. So my weight on the moon would be 0.165, and my weight on the Earth is 172 pounds. And so when I multiply those two things together, I'll just bring up a handy dandy calculator here. I get 172 times 0.165, 28.38 pounds. That's not bad. It's a little factoid you can carry around. And what's neat about this is that this formula for your weight on the moon will be true forever. The formula will, not your result. Your result will change with your weight. So as you gain or lose weight, obviously your weight on the moon will also gain or lose. But this formula that we've created will stand forever, at least until the moon disintegrates or something like that. As kind of an additional problem or a more advanced problem, even though it doesn't look so advanced, it's more of a concept mastery problem involving direct variation. We're going to use the fact that we know that two variables vary directly with one another to complete a table of values. So if you happen to know that x and y vary directly with one another, you can actually fill in this table of values as long as you have a link between x and y. And if you read through the table, most of these data points do not provide a link except for these two right here because they're directly linked to one another. Right? You plug in 5, you get out 1.5. So that will be our link. So if y varies directly with x, we know that y is equal to some number times x. Or in other words, that y over x is k. Remember, direct variation means that the ratio of those two values for the variables is always constant. So I know that y over x will always be some number k. So let's plug in this value of y, this value of x here. So y is 1.5 when x is 5. And we'll simplify this down. I'm going to multiply top and bottom by 10 to get 15 over 50. And then I'll reduce this fraction. Both of these numbers are divisible by 5. So that's 3/10, or in other words, 0.3. That's what our constant of variation is. If you need to slow down the video, you can. Just press pause. But basically all I did was multiply top and bottom of this first fraction by 10 so that I can get rid of that decimal in the numerator. And then I divided top and bottom by 3. And this is equal to 0.3. So now that I know that y is equal to 0.3 times x, I can use that to fill in the rest of the table. For example, this first x value is 2. So the y value corresponding to it should be 0.3 times 2, or in other words, 0.6. I'm going to drop down a couple. This x value of 12 down here is just 0.3 times 12. That's the y value corresponding to it, and that'll be a 3.6. And then to find the x values for these two y values, well, again, I know that if the y value is 2.4, it's related to x via that formula. The y is equal to 0.3x, so 2.4 is equal to 0.3x. If I divide both sides by 0.3, I will get that x is equal to 8. And finally, this last one, I have 4.5 is equal to 0.3x. If I divide both sides by 0.3, I should get that x is equal to a 15. So all you need is some link, some pair, basically, that you have both pieces of information for to create that link between y and x so that you can find the constant of variation. Now we're going to get into the more realistic examples. It's often not true that things vary just directly with one another. They vary directly with a power or a root of a variable. So, for example, y varies directly with the square or the cube or the nth power of x if y equals kx squared, or y equals kx cubed, or y equals kx to the nth power. If y varies directly with the square root of x, then we know that y is equal to k times the square root of x. If it varies directly with the cubed root of x, then it's y equals k times the cubed root of x, and so on and so forth. It's the same language, the same process, essentially, that we were doing in the previous examples. It just affords us the opportunity to work with more realistic examples. While the weight of a person on the Earth varies directly with the weight of a person on the Moon, the gravitational pull of the Earth, it does not vary directly with the gravitational pull of the Earth in truth. Taking an example here. This is a very famous example, pendulum examples. The period of a pendulum varies directly with the square root of the length of the pendulum. Now, the period of a pendulum is the amount of time it takes to go a full swing. Let me do this in red, actually. A full swing means back and forth. So from left to right and right to left would be one period. Okay, so there and then back. That would be one period. And the length of that period, or the time it takes, is directly proportional with the square root of the length of the pendulum. What this means is, if we let p equal the period, we know that the period is equal to something times the length of the pendulum. Well, no, not really, because it's not varying just directly, it's varying directly with the square root of the length. It's not just p equals kl, it's p equals k times the square root of l. That is our overriding equation here. Now notice in this case I didn't give you any information about this pendulum. I didn't tell you what the period is, nor did I tell you how long the pendulum is. because I'm not actually asking you anything with numbers. I'm asking you a more conceptual question here. In order to double the period, how would we have to change the length? In other words, here we have that the period is equal to k times the square root of L. Well, if that is true, what would happen to L if I were to change P to twice P? This could be a very tough problem, so I first want to start by encouraging you to look at how L is related to P, as far as right now we see that P is equal to K times the square root of L, but can we solve this for L? In other words, can we say that we could divide both sides by K to get this, and then we can square both sides? And the answer is absolutely. We could actually, this is pretty okay. We could say that if the period is P, then L is just going to be P over K squared. That quantity squared. That's what L is going to be. The question now is, what happens if we doubled the period? What would that happen? What would happen to the length? So instead of introducing a new variable, I'll just write new length, just to keep it more language style. Now remember, the length is just equal to the period over K being squared. And what we're going to do is double the period. And if you take a look at this, this is actually going to be, well, 2 squared is 4. And I'm not going to square the P or the K yet. I'll just leave the P and the K inside the parentheses. But you should be okay with me saying, well, 2 squared is 4. I'll just pull that out front. And then leave the P over K still inside there. And if you take a look at that, the new length, if I double the period, the new length is just going to be 4 times, well, wait a second, P over K being squared is just L. 4 times L. And let me highlight this. If you notice, this P over K being squared right there is L. So, turns out if we double the length, we have to quadruple the length. I'm sorry, if we double the period, we have to quadruple the length. And that's how it generally works with most objects in real life, is that since they're not just directly related, they're usually directly related with the square root of something or with the square of something. Adjusting something, the one variable by, let's say, twice its amount, usually manipulates the other variable by quite a bit more or quite a bit less. Not just a direct relationship. Now I understand that this example generally takes a lot of thought, so I want you to actually pause this, rewind it, read through it a few more times, really try to get what happened there. It's not the typical example, it's a more high-level example, but I want you to spend some time on it. For this next example, we'll do a web-based example, so let me go to the web here. According to suncatchersolar.com, which is, I guess, a solar site, and they're selling wind turbines and stuff like that. If you scroll down a little bit, they tell you the power output of a wind generator varies directly with the blade swept area. Now they give you some other explanation. It turns out wind energy varies directly with the cube of the wind speed. Wind energy varies directly with the cube of wind speed. So let's go ahead and use that information to create an equation. I quickly just wrote down the information they gave me. I'll let E equal the wind energy, equals, varies directly with, means equals some number times, the cube of the wind speed, and I'll let S equal the wind speed there. So the cube of the wind speed. So the energy equals some number times speed cubed. Now that we've found the formula, let's suppose that we want to produce 96 watts of power, and when we want to produce that, the wind needs to blow at 20 miles per hour. That is our link to allow us to find what K is, the constant of proportionality. We know that when the energy is 96, the speed of the wind has to be 20. And now we can solve for K. This implies that K is equal to 96 over, let's see, I think that's going to be about 8,000. which is equal to 0.012. So I know the constant of proportionality is 0.012. So let me rewrite my equation here. I'll rewrite it in blue just to denote that it's our final equation. And now the question that I'm asking is how fast must the wind blow in order to provide 1,000 watts for some event? So let's find out how quick the wind must be blowing. Let E, the energy, equal 1,000. And solve this equation for S to find the wind speed. So divide both sides by 0.012 and take the cube root, and you'll find that the S is equal to the cubed root of 1,000 divided by 0.012, which is not the proper way to write this. So using a handy dandy calculator, you can find out that this is equal to, I'm just typing into my calculator actually. I should have pressed pause, but I'm lazy. I get 43.7 roughly. Miles per hour. That's a pretty brisk wind if you want to generate 1,000 watts of energy. So you can already see if you're going to argue with somebody about possibly providing or putting a windmill on your home to provide energy, you can see that somebody will say, listen, that's not going to actually provide all the energy for your household, and it's reasonable to see why. Unless you live in a hurricane ready zone, this is not the only method to produce energy for your house. It's not very viable. With all that being said, I'd like you to try something. I'd like you to go out and look for a law of physics or anything like that expresses two variables being directly related to one another, either via cubes or squares. They could be directly varying with the square of something, directly varying with the square root of something, whatever it is. There are tons of laws in nature that directly vary with one another. Okay, so participate in your own education and use this as an opportunity to explore your world and to figure out kind of some stuff that you may have never known. If you enjoy music, find something in music where just all you have to do is Google it. Find something that in music that relates to variables via a direct relationship. If you're into ice skating, there might be something about the force of friction, the frictional coefficient for ice and metal, whatever it may be. So there's a lot of things in the real world that you can use direct variation and variation itself for. The next lecture will be on about inverse variation, which won't be as long as this because the fact is we will have some experience with variation at that point. But definitely get some more practice on this before you move on to inverse variation.